This video is about regression. We're going to limit the scope of our discussion of regression to linear regression. In other words, regression when the relationship has a linear form. The objective when we're doing linear regression is to take that linear relationship between the x and the y, the explanatory variable and the response variable, the independent variable and the dependent variable. We're going to take that relationship and we want to actually quantify it. We want to do some math to put some numbers on it and make it useful then for predicting a response if we're given a value for the explanatory variable or the independent variable. So here is what we do, okay? We are going to take our scatter plot, and you see here these blue dots are the scatter plot, and we're going to fit what we call a regression line to that data. And we're going to do it in a way that we get the best fit for that line to the data. And then we can predict from that line. Because then we can say on average things are going to fall on this line. So though not every data point falls on that line, but on average we can predict that that's about where something will fall. Okay, and we'll talk about the strengths and the weaknesses of doing that as we go along. So this is a prediction of the number of new birds joining a colony based on the percentage of adults returning. So the least squares is the method that we use to get what we call the best line. We get it as close as possible to the data points in the y direction because the y's are what we're trying to predict from it. And so we're going to use a line where we minimize the sum of the squares of the vertical distances of the data points from the line. So you take the distance of each data point from the line in the vertical direction, so how much above or below the line it is. And you square it, and you add them all up together. We want that to be the smallest number possible. Okay? So that's what the least squares part of it is. Now the formula for a least squares regression line is given by this equation. Y hat, the y with a funny little caret on top of it is called y hat. Y hat equals a plus bx. So you might remember from the graphing that you did in an algebra class that a in this equation would be where it crosses the y-axis, the y-intercept. And b in this equation would be the slope of the line. So if it's a positive relationship, b will be a positive number. If it's a negative association, b will be a negative number. Now, b is not going to be the correlation coefficient or the correlation that we did previously. They're not the same thing, but their signs are always going to be the same. So for that picture that we looked at with the new birds returning and the new birds coming into the colony, we can calculate a regression equation given by y hat equals 31.9343 minus 0.3040x. So where y hat is the average number of new birds for all colonies with a certain percent returning. So for all colonies with 60% returning, we predict the average number of new birds would be 13.69. We get that by plugging in 60 for x. Okay? So if we know that an individual colony has 60% returning, we're going to predict the number of new birds based on this average number of new birds, 13.69. So we could predict, you can't have 0.69 of a bird, so you might predict that you would have 14 new birds in just that colony. So where do we get the A and the B in our regression equation? Remember, the regression equation is y hat equals A plus bx. Well, we get B first because we need B to calculate A. And to get B, we multiply the correlation R times the quotient of the standard deviation of the y's over the standard deviation of the x's. And that gives us our B. Now once we have that, we take that B, whoops, we plug it in right there to get A. So now we take that B and we multiply it by the mean of the x's. We subtract that from the mean of the y's, and that gives us our A. So let's look at what it looks like to calculate one of these out. You will be using your calculator for the most part to do regressions, but you need to see what it looks like all done out. Okay, back to that regression calculation that we did with per capita GDP and life expectancy of these, 10 countries in Europe. Okay? So when we were doing regression, we did this case study and we figured out the mean, we figured out the standard deviation for both the x's and the y's, and we used those numbers to figure out the R, the correlation. So we have all those numbers calculated from those to plug in to find our B and our A. So here I've given you those 5 numbers that we calculated previously. And it might be a good check to go back to the previous slide and actually calculate them for yourself. See that you know that you can get those numbers. And then we're just going to plug them in. So we're going to put R, S sub y, and S sub x into the equation for B, and we'll find that B equals 0.420. And then we'll take that 0.420 and plug it into the equation for A, along with y bar and x bar from up here. We plug all that in. We'll get 68.716. So y hat equals 68.716 plus 0.420x. That is our regression line. That is the equation for the line of best fit. Now the coefficient of determination is the last thing I want to talk about with regression, because it's going to measure the usefulness of the regression prediction. So we can certainly put a best fit line, no matter what our R is. We can write a best fit line, and we can make predictions off of it. But how useful is that actually? How close are we? How much does this variable influence the response variable, so that we can say, yeah, the influence is strong enough that we can make a pretty strong prediction? So for that, we use R squared, the coefficient of determination. And it actually is R, the correlation, squared. So if we square the correlation that we get, that will tell us what fraction of the variations in the response variable values are explained by the explanatory variable we've used for our regression line. So if we have a regression coefficient for our regression, if we have a correlation coefficient for our regression of 1, that means our coefficient of determination is 1. In other words, all of the variability of y is explained by x. That prediction is spot on. If we have a correlation of 0.7, that gives us an r-squared of 0.49, which tells us that almost half of the variation can be explained by that one variable. So that's what the coefficient of determination does for us. If we ended up with an r-squared of, 0.4, well then it's not a very useful prediction because so little of the influence in the change of y comes from the line that we have drawn using x as the predictor.